So, second session of our coverage of power series. So, last week we had a look at using the Maclaurin series, which focuses on power series for a function focused on the point where x is equal to 0. A condition of using Maclaurin series was that the function you're trying to create a power series for exists where x is equal to 0, otherwise you can't use it. So, as we also discussed last week, the function ln x, that should have, does not exist in there where x is equal to 0. So we couldn't use the Maclaurin series on the function ln x for that reason. So we need to use the Taylor series, which doesn't have that condition imposed upon it. Taylor series defined as f of x is 0 and e to the which we and we will expand to f of x being the function value at a times the derivative of a multiplied by x minus a plus the second derivative at a multiplied by x minus x over 2 factorial and so on. Yeah, if you're asked to do Taylor series, the example expansion will be there. I would more than I think I'll put it in that form, because that's the way that you, rather than in that. All right, and that will be dot plus 3 dots to show that that expansion carries on in the same fashion. Okay. So, if we return to the function that we couldn't do last week, the function ln x, and we'll choose to focus on that function around the point where x is equal to 1. So we'll let a equal 1. So instead of focusing on where a is equal to 0 in the Maclaurin series, we're going to choose a different suitable point to focus on where a is equal to 1. So what we need is the value of the function ln x, so we do ln a, so we want the natural log of 1, which is equal to 0. Now, we need now to differentiate these terms and find out their value at a, where a is equal to 1. Right, so I'll let you do that now, similar to what you was doing last week. So we need to differentiate ln x, find the second diff, third, fourth differential. Once you get to the red line, I'm saying, can you see a pattern? Yeah, to the results. And then under the second red line, can you write a general rule for that to happen? Yeah. Right. So differentiate. This being equal to 0, by the way, means there's no constant in the power series. When we differentiate ln x, we get 1 over x, which we can write as x to the minus 1. Yeah. And if you go through the process here of writing out in longhand what the differentials are, so that becomes minus 2. And then we bring minus 2 down, so we'd write that as minus 2 times minus 1, x to the minus 3, which I'll write it over here, which we can write as 2 factorial x to the minus 3. here, we're now going to multiply 2 factorial by minus 3. So that'll be minus 3 factorial x to the minus 4. And then there's a pattern there now. This one is going plus and minus each time as a pattern. So that must be 4 factorial x to the minus 5. Minus 5 factorial x to the minus 6. And once pattern we like. So x to the minus 1. So we're looking for a to the minus 1, which is equal to 1 to the minus 1, which is equal to 1. Yeah. We're looking for minus 1. Sorry? Minus 1 factorial, yeah, if you follow it through all the way, times 1 to the power of minus 2. And that equals minus 1. Two factorial. Yeah. I'm going to write it like that. Jake, do you agree? 2 is 2 factorial. Yeah. This is minus 3 factorial times 1 to the minus 4. Yeah, which is minus 3 factorial. Yeah. So there's a pattern arising again there that we can carry on, because this is going to be 4 factorial minus 5 factorial and so on. So can we write a general for fn x, the derivative, on this side? This is the 6th derivative, and it's got minus 6 there, and it's got n minus 1 there. Keeps changing sign as well. n minus 1 factorial x to the power of minus n. Nearly there. What doesn't it deal with? Deal with the change in sign. Okay, we'll have a look at that in a minute. What about over this side? Can we get as far as that over this side? Fn of a is equal to, well, that's going 4, 5, 6, change in sign again, factorial all the time. So this is the way we can get a general rule for this bit on this side. This is the derivative, and we got minus 5 factorial. So we're looking at n minus 1 factorial to get the number bit. Again, we need to deal with the change of sign. So if we look at minus 1 times n, as n goes, when n equals 1, what does that equal? Yeah, n equals 2, what does it equal? 1. N equals 3, minus 1. Yeah, so that's changing sign each time. But when n is equal to 1, we do that. Sorry? A minus here. No, where? Here. No, that won't change. What value of n will give me a plus 1? The first value of n starting from 2, yeah. So how can this minus 1 to the power of n gives me minus 1. So I want that to be 2. So when n is 1, how can I make that 2? Plus 1. Yeah, if I do minus 1, n to the n plus 1, then it goes when that equals 1, when n equals 1, that equals minus 1 when n equals 2, and so on. I'll keep changing the sign every time. So if we put that in front of fractions, we've got a general solution. See that or not? Yeah, because that's going to change the sign of these each time. So if I put minus 1 to the power of n plus 1 there, put the same in here, that's a general rule for finding the result, finding the derivative on left hand side and finding the value of that derivative at a on the other side. There is a caveat to this. Not for first term, the lnx term. So it doesn't find that one. Yep. But it finds all the derivative ones, but not the initial term where original function lnx doesn't deal with that one. That's separate. Okay. Yeah, sorry. There. Yeah. Moving on from that, if we take the general rule that we've just now established, this one here, minus 1 to the n plus 1 times n minus 1 factorial, back into this Taylor series. Yeah. We know that we've got 0 for the first term because ln1 is equal to 0. Okay. And then we've placed our general term for fna. That's what we've in here over n factorial, like so, and then we can expand that. So 1 minute, we need to use an example, sort of simplify. When x equals 5, sorry, when n equals 5, we would have equals 0 plus the sum of minus 1 to the power of so we've substituted in for the example where n is equal to 5. Okay, now what is, if we divide through by 4 factorial, we then get 0 plus minus 1 to the power of 6. Divide 4 factorial by 4 factorial is, divide 5 factorial by 4 factorial, what are we left with? What do you multiply 4 factorial by to get the 5 factorial? So you're just left with 5 on the bottom. Yeah, and then that's multiplied by x minus a to the 5 over there. So this is simplification. We can now write a simplified Taylor series for this function like this. X equal 2 naught and infinity over n to the n. Well, you just to simplify, Dominic, if you do no, no, because all of 4 factorial over 5, aren't you? No. Yes. Sorry. Yes, you could. That's not. The reason that's not as clear. If you've got factorial notation. the video on. So what we're trying to mimic is y is equal to ln x. As you can see, it doesn't exist where x is equal to 0. It shoots off to infinity. You get an error on your calculator. So we're going to try and focus on the point where we've focused on the point where we've let I equal 1. So we're going to focus on this there where x is equal to 1. We've put the power series in. Y is equal to x minus 1 is the first term. Yep. All we got is a straight line. Is it plus for the first one or minus? Minus x minus 1 power of 2, and all of that is over 2, yeah? Right, so you can see I'm moving in line with the function, yeah, around that point where x is equal to 1, because that's what we set a equal to, yeah? And then the plus brackets x minus 1 close brackets to the power of 3 all over 3. Next term is minus x minus 1 to the power of 4 all over 4. So prim function around that, and if 4 terms, the closest will become to the act. Knowing that, if we go back here, if we use the infinite series, then it's a perfect fit. Sorry? Let me give you, we'll look at the next one to do, and I'll see if I can find out how the notation works in Desmos to show that that's a perfect fit. I'm not sure if I really know how to do it, but I'll have a go. Alright? So, and there's a graph in the notes similar to that, so I don't know how many terms, but probably 4. Right, we're going to get you have a look at Taylor's to determine the first 5 non-zero terms for the function fx is equal to 2 sine x. Remember, we done the sine last week, but we used the Maclaurin series and focused on where x is equal to 0. We're going to do now, show we can focus on the sine function at a different point. We're going to focus on the point where I is equal to pi. So go through the series process for 2 sine x, where I is equal to pi. Alright? Yeah, looks like it. We got fx equal to sine x, so over this side f at a equal to 2 sine of pi, which is nothing. Yeah. First differential is 2 cos x minus 2, yeah. Second differential, minus 2 sine x. The value of that at a is equal to 0 shortcut it a little bit. Third differential. Two. And so on. Yep. So these go -2, none, 2, none, -2 as we carry on. Yep. All agreed? So you can write out that Taylor series. First term is 0, so there's no constant term. Then we got -2, x minus pi. The next term, squared term is 0. So the next term is +2 x minus pi to the power 3 over 3 factorial. -2 x minus pi to the power 5 over 5 factorial. That's 3 non-zero terms. +2 x minus pi to the power 7 over 7 factorial. -2 x minus pi to the 9 over 9 factorial. So every odd term is there for that sine function. Yeah. Find what? Well, how do you get to this? Where does this come from? From the I'm not sure what you mean. How did I get that result? By putting the constants in the power series. Sorry? Yeah, by inserting them in the power series. All right? So I'll graph that one in a minute. On the next page, Taylor series to determine for the first 5 non-zero terms of f of x is equal to 2 sine 2x. So change the frequency there with the sine wave. We're going to focus on the point where a is equal to pi over 2 this time. Right guys, in the board notes which I'll put on the website, I've just added a screenshot of those two graphs superimposed on each other and made the note that the black one is the function y is equal to 2 sine x, and the orange one is where the y is equal to the power series for the 5 non-zero terms that you discovered. So I've just added that to the board notes for this week. How are we doing with the function 2 sine 2x? what is that function equal to when a is equal to pi over 2? What's the result here? Times the sine of pi. Zero, innit? Everyone agree? First term 0. First derivative. Four cos 2x. What's the matter, Dom? Are you done? Two. In the entry in the table, the 2 in front of x is the a, isn't it? So we take that out and multiply, but leave it inside. So we're looking at 4 times the cosine of 2 pi over 2. Sorry? Second derivative. Minus 8 sine 2x. The result of that is 0. Third derivative. Minus 16 cos 2x. Fourth derivative, value of a is equal to plus 16. Is there a pattern yet? 0. Next one. Minus 64. 0. 356. So we got 5 non-zero terms now. We've got 1, 2, 3, 4 non-zero terms. Yep. Therefore, power series is there a constant term? No. Yeah. Then we got minus 4. X minus pi over 2. Next term is, next term 0, so the next proper term is plus 16, isn't it? X minus pi over 2 cubed, yeah, over 3 factorial. Next one is negative, and that was minus 64, wasn't it? Times x minus pi over 2, power of 5, well 5 factorial, plus 128, no, next one after, 252. So there's 7 over 7 factorial minus 1024 x minus pi over 2 to the 9 over 9 factorial. What do you think would happen if we done cosine instead of sine? What do you think would change? Try cos 2 cos x. Just start finding the constants. See if you can see what the difference is. I'll graph this one up. So for the video, if we graph that power series against the actual function on here, the blue one is y is equal to 2 sine 2x. Green is power series five non-zero terms. So when we done sine functions last week with the Maclaurin series, we were always focusing on this point here, but what we've done this time is focused on pi over 2, that point. Yeah. So we shifted the focus by using the Taylor series and selecting a focus point of where we want the value of a to be. Alright, so Maclaurin series is just a Taylor series where a is equal to 0. Alright, in your handouts this week, there's I've slotted in, it's not around this topic, as a typical exam question around the topic we done 2 weeks ago. Giving you an indication of where marks might be given. Okay. What is the focus around there? That typical exam question. Required to evaluate that function. Using suitable techniques, demonstrate that the integral above can be written as that there. So what have you got to do to get from that first function to the one underneath it? What's the process? That's a what? Partial fractions. So the first bit is asking you to demonstrate that using partial fractions techniques, you can separate that into those 2 partial fractions there. And then the rest of it is, can you find the definite integral for that function using normal integration techniques? And then once you've found the definite integral, can you apply the limits and find the evaluate the definite integral between 4 and 7. Okay, so it's a typical exam question, 25 marks. So it's in the long answer section of the paper. All right. So you can have a go at that, and then perhaps we'll take a look at the solution next week. All right. If not, I'll put a solution up on a website.